Hello, my name is Daryl Jarman. I am a senior computer scientist at Adobe.
And my name is Scott Hunt. I'm a principal scientist at Adobe.
And our other author is Dave Towey at the University of Nottingham. He's not with us today. Um, uh, Before we start, we want to say how glad we are of this opportunity to present this short industrial paper at this conference. We feel it's a great honor. We're sad that we can't meet the ICPC community in person this year, but we understand that due to the pandemic, this is the right thing to be doing, and we're fully supportive of that. And we hope everybody stays safe and healthy, and hopefully in the near future, we'll all be able to meet. We have a summary that we're going to have here at the beginning, but before that, I actually wanted to just make a comment on behalf of Adobe that we have the position that we believe that everyone deserves respect and equal treatment, and we stand together with the Black community against hate, intolerance, and racism, and we feel strongly about this, and we feel it's important to make that message heard, and at Adobe we are also following that up with actions. Here's a quick summary, 1-minute summary. We did some differential testing, which is fantastic for customer reported regressions. It's the best thing we ever found for that. The difficulty with difference testing, though, is it generates so many differences, and it can only tell you that it found a difference. So it can't tell you that it was the difference that you intended. So if you had a bug fix, it can see that you've changed some behavior, but it can't tell you whether you did that properly or introduced a new bug. So how do you handle all of these differences? And we tried two things. The first thing we did is we used some concepts from association rule mining, the market basket analysis actually, and we're very successful in grouping test cases into similar, not even similar, exact behavior. Then we could take a group of test cases that had the exact same behavior and only have to verify a few of them manually. And this probably reduced our workload by 90%, and fantastic success. But as we went forward, we realized that we could probably do better by not grouping solely on behavior, but also on how the code changed. Because when you have 100 different changes in a release, it's entirely possible that some of those changes or some of the combinations of those changes could have very similar behaviors, and it would be important to trace back into the code what that was. So that's what we're going to talk about, and also where we would like to get help from the ICPC community to solve some of the issues that we found. Here's the paper with our authors on it, and I hope it's not considered too self-serving, but here's the other paper on grouping that we did using association rule mining. And we feel that these two are related and they're not separate. And so it might be of interest to know how we group so that we can know how we can take slicing and add to that. Scott's going to talk for a minute about our reporting API, which is the project that we did this experiment on.
Yeah, so Daryl and I worked together on the Adobe Analytics Reporting API, which is a layer that sits in between our web interface and our data stores. It's been evolving over 20 plus years, which means it's full of cruft as well as good stuff. Let's see. It's divided into, it's divided into hundreds of different reporting classes with literally thousands of independent parameters that can control all of the various reporting options that we make available to our customer. And change certainly over this 20 years has been a constant. We see graphs here of lines of code changed. The lines of code changed is a logarithmic scale. And then the second graph here is our changelog items and our number of commits in our repository. And we just constantly make changes, which opens up lots of possibilities for regressions, which our customers dislike. Over time, we have tried various testing methodologies. We've hopefully gotten better at it over time. I mean, certainly at the beginning, we were testing just the things that we thought we had changed. However, you end up missing stuff that you thought you didn't change. And of course, I mean, inadvertently, we tried customer reported testing, where we wait for our customers to tell us what's wrong. And that's obviously the worst kind of testing. So we moved on to this differential testing, which has provided great benefits for us. However, it also provides us with a lot of noise during our testing, and it makes the time to determine that you have actually only made the changes you intended to make difficult to identify.
Yeah, Scott's exactly right. We only have 4 minutes left, so I'm going to go through this fast. We captured 10 million real customer reports, reduced those to a small set of about 40,000 to run. We could only run about 3,000 of those in the beginning because it would produce so many differences. It would take an entire week to manually verify them. After we added the difference grouping, we got to where we could run all 42,000 and verify our results in a day. And so it was a huge success. We greatly reduced our customer reported issues, and we were quite happy with this for quite a few years. And then we got to thinking about this situation, and we realized that we could probably do better. What we were grouping on was actually behavior. And what we would like to be grouping on would be the actual code changes themselves. And so program slicing became a metaphor that we thought about when we were thinking how to do this. We have access to the code, so why not put some code coverage type instrumentation in there and look at what happened. Of course, instrumenting the entire project and running it was completely out of the question because it huge amounts of information, most of it irrelevant, and just too expensive to do. So what we decided we needed to do was to do partial execution tracing. And this is where the program slicing concept came in for us. The program slice takes a slicing criteria, as you all know, way better than me for sure. And it says, give me all the paths, all the execution paths in this code that will go through these lines of code, this slicing criteria, and have some kind of effect on that. And so we thought, well, let's just take all of our differences between our known good one and our proposed fixes and use those differences as the slicing criteria. So to identify the slicing criteria, we just do a simple diff through our directories, identify the files that have lines changed on them, go through those files and insert statements that record some information about the lines as execution passes through, pass that up through the reporting structure of the API, log that information out. After collecting that, you then have a difficult problem there, number 4, which is how do you take all that information and put it into some easily understandable form? And this is a problem we've never really solved. And we're hoping that we're sure that the ICPC community has had to deal with this visualization issue because there's just so many traces, and how do you know what you're looking at? And it's one of the things that we never really solved and would really like to get some help with. One way that we did decide to use to cut down on the amount of information was to set different levels of recording to be logged, information to be logged at various times. So we might only record that we entered a function and nothing else. If we're running something really quick and just wanted to know we hit a function, all the way down to number 4, where we would record values at every line of code and have that information almost like, exactly like automated debugging, so that when you looked at a difference, you saw a complete debug trace of the values before and after every line of code that changed. And we feel that this was really helpful in helping us get from behavior to actual code. Now there was no need to infer that we had captured the behaviors we wanted to. We could actually watch the code being executed. So the two challenges still remain for us is how do you do this with a small enough footprint that you can actually run things fast enough? And how do you then take that information and visualize it? And then, of course, the one that's kind of inferred in both of those is what information is the right information. We're out of time. That's 10 minutes exactly. So we just want to say thank you on behalf of Dave and Scott and myself. Scott, anything else you want to contribute?
Nope, that was great, Daryl. Thanks.
Thank you. And thank you, ICPC community.